of the second session. So due to unavoidable circumstances, today's schedule has been revised, and we are delighted to have with us our esteemed speaker, Dr. Ashwini Kumar Cherukuri, professor at the School of Computer Science, Engineering and Information System, VIT Vellore. With over 24 years of academic and research experience, Dr. Cherukuri's expertise spans machine learning, information security, quantum computing, and post-quantum cryptography. He has published more than 200 research papers with 4,700 plus citations and an H index of 34 on Google Scholar. He has also successfully executed multiple funded research projects worth over 10 million US dollar, and he has guided 8 PhD scholars and several international interns. He has been continuously recognized since 2020 among the top 2% scientists in India in AI and ML by Stanford University researchers. In addition, he serves as adjunct professor at UCSI University, Malaysia. He is on the editorial board of several international journals and has received prestigious honors such as Young Scientist Fellowship, Inspiring Teacher Award, and Educator Excellence Award, and also a NAC peer review committee member who has visited several reputed colleges across the country. Today, he will be delivering a session on Introduction to Quantum Computing. It is my great honor to welcome Dr. Ashwini Kumar Cherukuri. Over to you, sir.
Good evening, madam. Am I audible?
Yes, sir. Yes, you are audible.
And my slides are visible?
Yes, sir. Your slides are also visible.
Okay, so good evening, everybody. It's my pleasure to deliver this lecture on quantum computing on the occasion of ATAL Faculty Development Program on Next Generation Technologies in Action on the specific topics of generative AI and quantum computing, organized by Sadhu Vaswani Institute of Management Studies for Girls in Pune. So it's my pleasure as well as honor for receiving this invitation. And in the next 1 hour, 30 minutes or so, I will be delivering my presentation introducing various aspects of quantum computing. I understand from the organizers that the participants are quite enthusiastic, and as well as they are from different backgrounds, including management and other branches. So I will be delivering my lecture. I'll try to keep it less technical, as well as I will try to give as many examples as possible and then keep the presentation in a lighter manner. So before I proceed further and introduce actually the quantum computing, I was listening to the questions asked by some of the participants to the previous speaker. I understand that there are faculty from computer science, and I was told that there were participants from the management discipline also. So considering that, I have fine-tuned some of my slides. So before we proceed to the actual topic, all of us know, that when we consider a coin and which does not balance on its edges, it has two faces. So it has a head and it has the tiles, right? So imagine that there is a single coin lying on a flat surface. Then it can face towards its heads or it can face its tiles up. Now imagine if I have two coins. If I have two coins, obviously I will have four states. In the sense, both of those coins can face with their heads up, or one of the coin can face its heads up, or else the other coin with the tiles up. Otherwise, one of the coin facing its tiles up and the other coin facing its heads up. Otherwise, both coins facing their tails up in the in the last scenario. So there are about 4 possible scenarios, meaning I am calling that scenarios as 4 possible states. So there are 4 possible states. If I have 2 coins, they would be facing these heads or heads tails or tail heads, tail states. So there are totally 4 possible states if I have 2 coins. Now imagine if I'm adding one more coin, that means third coin, then how many such combinations I would get, or rather scenarios I would get, or rather states I would get. Obviously, I would get 8 possible states facing one coin head, another coin head, another coin head, so on. I may have the last scenario, all coins facing their tails up. So these are the possible states, meaning I have 8 possible states with 3 coins. So if you closely observe, I am getting 2 coins. If I have 2 coins, then 2 square, which is 4 possible states. If I have 3 coins, it is 2 cube, having 8 possible states. Again, if you closely observe, the base value indicates the either of the cases, head or tail, that means 2. Then total number of coins, it is 3. It is in the power. So totally I'm getting 8 possible states. Similarly, you can observe the same. I have head or tails 2 and then 2 coins. Then you have 2 power 2, which is 4 possible states. Now, why we are discussing about this? Somebody may get a question. We have some reason why we are discussing this. Now imagine if I proceed further. Imagine if I have n coins, then what would be the total possible states I would have? 2 power n possible states. Right, why we are discussing this? Again, I will answer that doubt in the upcoming few seconds. Again, imagine I have a 6-sided dice. When you look at that standard dice, when we are playing, the dice can have either of these, the states facing up, either 1, 2, 3, or at the end 6. So meaning the possible states of a dice are 6 states, 1 to 6. Imagine if I have 2 dice, you can see all possible states of 2 dice represented in this particular diagram. So same thing we are putting in the form of a table. So dice 1, if I have dice 1 on column, another dice on the rows, so 1, 1, 1, 2, and so on. The same thing, I have kept it in the form of a table. Right. Now, so if you closely observe, since each die has 6 possible states, there are about 36 possible states for 2 dice. If we continue the same pattern, if I have 3 dice, obviously I will have 216, meaning 6 to the power 3, 6 cube possible states. Now, when we proceed like this, if I have n dice, totally I will have 6 power n possible states. So one we have seen with regard to coin, the other one we have seen with regard to dice. So again, if you observe, if you have coin, it is 2 power n possible states. If you have dice, it is 6 power n possible states with n dice. Now, why we are talking about this? We are talking this particular coins or dice to identify or to quantify how much information coins and dice can carry. What does it mean? So let us say, take an example. Imagine I have a rainbow. So totally there are 7 colors, and these 7 colors can be represented or encoded by the possible configurations of either 3 coins or 2 dice. Meaning what? If I want to encode all these 7 colors, I should use either 2 coins, 2 dice, or 3 coins. How can I use it? So let us say, imagine I have color red. Color red, I can encode it as head, head, head if I am using 3 coins. If I am using dice, I can encode it as 1, 1. Similarly, if I want to encode color orange, I can encode in the form of 3 coins as head, and tail. If it is dice, I can encode it as 1, 2. And you can proceed further: yellow, green, blue, indigo, and violet. Right? So this is how I am going to encode the colors of a rainbow. So meaning what actually I'm doing, if I have 3 coins, first heads, then tail, and then tail again, right? What it is going to represent? It is going to represent the color green. So head, tail, and tail, it is going to represent my color green, right? So if it is dice, I'm going to represent in the form of 1, 4, right? So if you closely observe, if I want to represent a particular color, if I am representing in the form of coins, I need 3 coins. If I am representing in the form of dice, I need 2 dice. So what this finally infer? A coin carries less information than die. Because of that, I need more number of coins, less number of dice to encode colors of a rainbow. So that is the reason why, if you observe, it takes 3 coins to distinguish the 7 colors of a rainbow, whereas I need 2 dice to distinguish the rainbow colors. What is all this giving a hint or a clue, or what is this is related to our current topic of quantum computing? The final conclusion is something with 2 states carries the smallest amount of information possible. What is that which is having 2 states in the world of computer? The classical bit, which is the fundamental unit of classical computer, which represents the information in the form of 0 or 1. In the coin analogy, either it is representing in the form of either head or tail. The classical bit represents the information with the 2 states, either 0 or 1, either off or on. Right? Everybody knows this. So conventional digital computers have only 2 states, which is 0 or 1. Okay, so what does it mean? What is that next you wanted to tell? Meaning, imagine if we have something else which can carry not 2 states, but rather more states. What it will do? It can represent my information in a smaller number of states. It can represent a large number of information. That's what we have seen with the case of 2 coins or 2 dice as well as 3 coins, right? So the fundamental basis or fundamental difference between a classical computer, quantum computer lies from this particular observation of a classical computer. We can say a kind of a coin like representing on, off, head, tail, whereas a quantum computer is like, with more number of states representing like a dice. Right? So it's a very, very, very primitive example, but to get a feel of something which is carrying us with the 2 states would carry smallest amount of information, whereas if it can have more number of states, it can carry large number of information. That's what is the basis of our entire quantum computing. If we observe the way the computers have evolved, especially all of us know that the modern digital computers have evolved after World War II. But if you observe during this evaluation, especially in the last 4 or 5 decades, we have a tremendous progress. But however, computers have come by the term of computing, it has come from a long way. Earlier, if you say computers, now present day we say computers, we all know the modern gadgets. But the first computers were people, and it's not the machines. The people were performing the computations and calculations. In fact, the term computer was dated back to early 1600s, before our digital age started, meaning those days computations and calculations were performed by the people. But even though we have humans were placing the calculations in the modern history as well, especially with the NASA the early days of NASA, where in which people were doing the manual calculations. And subsequently, post World War II and 1960s onwards, first mechanical computers, then electrical computers and electronic computers have taken the evolution, and they have taken the entire computing environment. Again, there is a huge history of the way these computers have evolved in terms of their sizes, in terms of the memory, in terms of the processing speed. There is a huge evolution that has come, and now from larger room sizes to handheld devices, we have the computers that got evolved. So in all these computers, or the modern digital computers, what is the fundamental unit? The fundamental units is a classical bit, which is the fundamental unit of representing, processing the information. So we can encode whatever the information we would wanted to encode, store, process using the bits. And fundamentally, we will use words, characters, and even pictures would be encoded and stored in the form of bits. But once you represent the information in the form of bits, we process those information using various logical operations, whereas for a computer, they are nothing but logic gates. There are several logic gates like OR gate, AND gate, NAND gate, like that. There are several logic gates. So from bits to gates, gates to registers, registers to circuits, we have various fundamental units or fundamental building blocks for the modern digital computers. Now, all that is fine. So this is all about evolution of computer. Now, every day we are listening the word quantum computer. So what is quantum computer? If you observe a classical computer is fundamentally based on or manipulating the fundamental physical properties and classical mechanical properties. And quantum computer actually uses quantum mechanics and quantum physics behind its computation, and hence it gives us massive parallelism, massive amount of parallel computing through quantum physical properties. What are those quantum physical properties? Superposition, entanglement, and decoherence, which are not there in the classical computers. So which are against the classical computers, quantum computers have this phenomenon, and because of which they have a huge, massive parallel computing power. And because of that, we have several advantages now. Again, there are several couple of disadvantages because of which the entire security community is little worried. And on the other side, there are various business use cases of this massive parallel computing where people are trying to leverage quantum computers and try to solve the problems that conventional classical computers are not solving. So meaning what? You have certain business use cases which can leverage this massive parallel computing, and there are certain challenges where computer scientists and others are trying to solve because of this massive parallel computing. So both we are witnessing today. Yes, now what are the features of this quantum world? Or in the sense we said, the quantum computers follow the physics that are coming from quantum physics. What are those features? If we observe, in a few seconds back, I said you are having fundamental unit of information is bit, and then we have gates, we have registers and all that to perform computations. In a classical computer, we perform these computations on real numbers. However, in quantum computers, the computation happens on the complex numbers. So those especially coming from the different branches of the management and others, we have in the number systems, we have natural numbers, we have real numbers, we have integers, but at the same time, we have certain set of numbers called complex numbers, wherein which you have a number having a real part and also has an imaginary part. So quantum computers deals with the complex numbers. In fact, real numbers is a subset of complex numbers. So classical computers are able to deal with only real numbers, but not complex numbers. But whereas the quantum computers, the base itself is the complex numbers. So quantum mechanics is different from the other branch of sciences because this is using fundamentally the complex numbers. Then the other features of quantum physics that is coming to quantum computing is computing from moving from single state environment to superposition of state environment. So this is another interesting keyword that every day we use, even whenever we are reading about quantum computing, the word called superposition. What is superposition? A superposition means, to understand that every object exists in a unique place, in a well-defined state, even when we are not looking at it. Although this is true for large objects, quantum mechanics tells us that it is false for objects that are very small. Meaning what? Say, take an example. I keep giving this, example whenever I give my lectures. So at the moment, I'm doing one particular task of delivering my lecture. At the same time, my brain is also doing several other thought processes, which includes, coordinating several things, right? So meaning what? If you look at if you look at a particular person as an individual entity or an object doing one particular task, but at the same time, if you look at the brain is doing multiple parallel activities or multiple parallel tasks. So meaning a computer, a classical computer at a given point of time would be performing only one particular task, meaning, processor would be executing one particular instruction coming from the operating system or the application. But whereas a quantum computer can perform a parallel activity of executing multiple tasks or multiple states. That's what is called superposition. So if we say that an object is in superposition, it is simultaneously in multiple states at the same time. Meaning, right, we say that I'm doing multiple tasks at a time, I'm doing parallel tasks at a time. So this is the exact word in the quantum computing called superposition. Meaning what? We are simultaneously in multiple states at the same time. At a given point of time, an object would be there in multiple states, right? So, but what happens when we say we are measuring that particular object from the superposition state? That object would get collapsed and called it will settle down to a particular well-defined state. So from superposition, it will settle down to a single state through the process called measurement, right? So take an example. Imagine when there is a lecture going on in a class, if you observe a student, physically the boy would be there, boy or girl would be there in the class, but they would be thinking multiple thoughts at a given time. But the moment we ask a question, the student will come to an alert and then try to focus on what we are asking. So meaning what? The brain is in a superposition state, doing, thinking, multiple activities at a given point of time. But the moment you post a question, it coming to a particular single state called, we call it as a measurement state, or we call it as a collapsed state. So that's the analogy that I can give whenever I give my sessions on this quantum computing. So superposition, meaning we are there simultaneously in multiple states at a given time. A measurement is nothing but when we observe or when we try to finally compute and calculate and measure the superposition state, it gets collapsed to a single state. And the next feature that is coming to the quantum computing from the environment of the quantum physics is moving from locality to the non-locality, right? So what is the fundamental notion or fundamental objective or fundamental basis for the current modern science is that we know that objects that are directly affected are only those that are near to those objects. Meaning what? In operating system also, we say that a particular memory location, if it is referred by a processor or an operating system, it is more likely that the nearby locations are also would be referred. So it's a called principle of locality. But whereas in a quantum world, we move from locality to the non-locality world in the sense that two particles can be connected, or we can also say the same connected word as entangled, even though they are at different places, even though they are at far different places. So we move from locality to the non-locality. This is one of the other feature that is coming from quantum physics to the quantum computing environment. Then another interesting feature that is coming to the quantum computing environment from the quantum physical features is we are going to move from deterministic laws to the probabilistic laws. Meaning what? Say, take an example. We are moving from, say, take an example. When we have an algorithm in a classical world, when we have an algorithm given a particular input, given a particular, the amount of time, an algorithm would execute and produce always the same result. If the same input is given, when we execute the same algorithm, it produces the same output. But whereas in the case of quantum, the output is not a deterministic output, rather it is a probabilistic output. So that is the reason why if you observe to which specific state a superposition state will be get collapsed when it is measured, nobody knows. So it's a probabilistic in nature. So meaning what? If I throw my coin, to the air, when the coin flips, it is kind of a superposition because it is flipping between head and it is flipping between head and tail. But when the moment you measure it, it would become either head or tail. But you are not sure whether it would come to the head state or whether it would come to the tail state. We do not know, right? So it's kind of a probabilistic. So here also the outcome would be probabilistic in nature. Again, we are going to have one more property called moving from certainty to the uncertainty. As I said, the outcome is highly uncertain in the case of quantum computing. So the laws of quantum mechanics also inform us that there are certain inherent limitations to the amount of knowledge that one can ascertain from a particular physical system. It is arised from a property called Heisenberg uncertainty principle, which says that there is a fundamental limit to the precision with which certain pairs of physical properties of a particle can be known simultaneously. This is called uncertainty principles. This is the fundamental definition. What does it mean? It indicates. Meaning what? If we more accurately we try to know a particle's position, then we will know less accurately about its momentum. That is what is a loose definition for the given uncertainty principle. What does it mean? So take an example. Imagine there is a train moving, meaning what? It has some momentum. Now I want to measure its position. When it is in movement, can I measure its position? No, train, car, or bus, whatever the object that has the momentum and it is moving, and if I try to measure its position, obviously I cannot measure. The moment I measure from the time that I was trying to measure to my actual measurement, the car might have moved because of its momentum. So meaning what? If it has a momentum, the less I would know exactly about its position. Right? That's what is called uncertainty principle, meaning which the more accurately we know about the position, then we know less about its momentum, right? Or even vice versa. I gave the example of the vice versa, right? This is the another interesting feature that is coming from quantum physics to the quantum computing environment. So because of all these features, quantum computing is becoming unique. So what are the features? Just to summarize, we are moving from real numbers to the complex numbers. We are moving from single state objects to the superposition of state objects. We are moving from locality to the non-locality of the entangled objects. We are moving from having a deterministic outcomes to the probabilistic outcomes. We are computing from a certainty environment to an uncertainty environment. These are the different features which are motivating factors or which are the basis for quantum computing. I hope all of you are able to follow. Are there any doubts so far? My pace is fine? My discussion is fine? Are there any doubts so far? Whatever we have discussed?
If anybody wants to ask any question, they can raise you can raise your hand. Yes, sir. We can.
Yeah, I see a couple of questions.
Yes.
Can you please explain any of the quantum algorithm like SHAR algorithm? Of course, I can explain, but now considering the time we have, SHAR algorithm is an interesting algorithm. I know this algorithm, is one of the fundamental algorithm which was proposed in 1992 or 93, where even people were not having any kind of quantum computer. So this algorithm is the one which is making many of our entire security industry sleepless, because of now today we have quantum computers. What this algorithm is trying to do is, it is trying to solve one of the fundamental problem in cryptography, where in which that problem is the basis for entire public key cryptography algorithms that are providing security to our online transactions, that are providing security for our digital signatures, etc., etc. So because of that algorithm, now all these public key cryptography methods, protocols, they are in danger. So, and that is what actually people are trying to build post-quantum cryptography algorithms. And now we are at a particular level of standards that have come recently from NIST, and the solution builders are trying to build protocols and the other security products from PQC standards that are coming from NIST. So SHOR algorithm is fundamentally an algorithm that is solving a problem called finding prime factors of a given number. It appears so simple in the sense that, just to give a glimpse of what is this algorithm is doing, imagine if suppose somebody gives you two variables like xy and asking you to find product of it. So you can always find very easily x into y. But what actually is the challenging factor is, if suppose somebody gives you z, asking you to find the factors of z, meaning x comma y, this problem becomes challenge. In the sense, this is a computationally easy problem. This is computationally tough problem. This problem becomes much more tougher if suppose somebody is asking you to find not simply x and y, but these x and y should be prime numbers, right? Meaning what? Asking you to find the prime factors of z. Of course, if suppose somebody gives you a single digit, two digit, three digit numbers, this is relatively easy. But what we are talking about the complexity in terms of numbers which are of 200 digits, right? Numbers which are of 150 digits. These type of numbers, even the current supercomputers also cannot solve. And because of that, the because of the SHOR algorithm, which is providing this solution to this problem, uh, you know, uh, in fact, on this particular premise, where in which we don't have solution for this, based on this particular problem, we have, the security algorithms from public key cryptography. And now, since the SHOR algorithm is solving this problem, all those algorithms are becoming vulnerable. So that's the point. No? That is the challenge. And entanglement example related to quantum computing, of course, I will talk about it in the next few slides. So yeah, I think people are fine. And sir, it's good that you are considering persons from management. Yeah, I think management, I would give some of the perspectives at the end before my concluding their talk. So as I said before, let us continue. Features of the quantum world, we have talked about it. So if you observe, the bit, we said fundamental unit of the quantum computer is the bit, which stores the information 0 or 1. Now, when it comes to quantum, what is that bit would be, how it would be, right? So if you observe for that particular purpose, if you notice an electron, which may have two spins, either it could be having a clockwise spin or a counterclockwise spin. But a quantum computer, you can think it as an electron which has a mixed state, in the sense. So take an example. I have a classical bit in the form of on, off. So when it is on, I'm saying it is 1. When it electric pulse, it is off, it is 0, right? When it comes to a quantum computer, you can see on the other side of the slide, where a small GIF image is shown. The how it actually gets implemented is through electronic spin. So in the sense, if you notice, that electron is in the form of both 0 as well as 1. So in the form of left spin and right spin. Another crude analogy I can tell is, kids play with the spinner, right? Widget spinner. So the spinner actually rotates, right? Either horizontally or vertically. You can think of a spinner which can actually rotate both horizontally and vertically. That's a kind of the fundamental unit called a qubit. So a quantum computer uses the qubits. Quantum computer uses qubits, which are the basis for storing the information, right? So in the sense that it has the blend of possibility of being 0 as well as 1, right? So as I said, in a conventional computer, it takes 4 separate calculations to run through all possible combinations of two bits. If I have 2 bits, 0, 0, 0, 1, 1, 0, 1, 1. So I have 4 separate calculations to run through all the possible combinations of two bits. However, in the case of quantum computer, you will have, so you can see here on the left side, if I have 2 bits, I have 0, 0, 0, 1, 1, 0, and 1, 1. I'm having all 4 possible combinations, but I have to go through them in a sequential manner. Whereas if you notice on the right side, if I have 2 qubits, I will have 0, 0, 0, 1, 1, 0, 1, 1, all 4 possible combinations at a time. You see the GIF animation, which shows 4 combinations of bits coming sequentially. On the other side, 4 combinations of qubits coming at a time, being available at a time to the programmer or to the user. Meaning what? If you have all 4 states at a time available to the programmer, we can do computations very easily, very faster manner. Rather than doing sequentially, we can do in parallel, right? That's the beauty of the qubits. So the concept or the theoretical analogy of these the qubits were there earlier. People were struggling. How do they implement it? But thanks to the technology from the various physics scientists, now people are able to implement the qubits having these properties through various physical the structures, right? So this is the quantum speed up because of the availability of all possible state at a time, right? Now the slide actually shows only 2 qubits or 2 bits. Now you can give the same analogy for 3 qubits, 4 qubits, or 5 qubits. The more number of qubits, more number of possible states, and all of them being available at a time to the user or the programmer or the developer or whoever it is, right? This is called quantum speed up, right? Now, if you closely differentiate the classical computer and as well as the quantum computer, in terms of quantum storage, you have bits which are manipulated through the electric pulses, whereas in the case of quantum computing, it is through the spin of electron in the form of qubits, right? So information, how it is processed, as I have already said, you have classical gates. In the case of quantum analogy, simple analogy to the classical gates, we have quantum logic gates. If you observe, next to the gates, you have circuits. In the case of conventional computers, all these classical circuits are governed by classical physics, whereas in the case of quantum computers, these gates are governed by quantum physics and quantum mechanics, right? How the information is represented in the form of either 0 or 1. But whereas in the case of quantum 0, it could be 1 or it could be both of them. That is the beauty, or that is the advantage that the quantum computers are providing. Now, any computer by means, it has fundamental mathematical theories. So if you observe, the Boolean algebra supported by so classical computers are supported by Boolean algebra, whereas in the case of quantum, they are the linear algebra over the mathematical space called Hilbert space. its complex number space is called Hilbert space. That anyway, it's a mathematical aspect. So next, if you observe the advantages, there is no limit of copying or measuring the signals in terms of classical computers. However, in the case of quantum, because of the availability of the all possible states, obviously the quantum computers are highly faster than the classical computers. In the case of the disadvantages, certainly the classicals are slower than quantum computers, right? But when you look at the quantum computers, they also have certain disadvantages as of now. There is a lot of noise. There is a lot of noise because of the external environment, and these quantum computers are prone to the errors because of the noise coming from the external environment, and hence they are fragile, right? So these are the basic disadvantages with the quantum computers. And now what people are developing is called noisy intermediate state quantum computers, NISQ quantum computers. Down the line, people are expecting that we will have noise-free quantum computers that we need to wait and watch, right? So these are again the slides which are talking about the fundamental unit of classical computers is bit. For the fundamental units of the quantum computers are called qubits. How do you say it is a qubit? It is represented through a notation called bracket notation. We write in case of classical bit, we write it as a 0 or 1. Whereas in the case of quantum computers, we write that the state of the qubit either in the form of 0 or 1 through this particular notation called bra and ket. Right? This is only for the notation. Those who are not belonging to the computer science or the other related disciplines, I think that for them it may be something new, but for the others of computers, I think these are this one. As I said, you have given a 2 qubits, you have all possible qubit states 0 0 1 0 0 1 1 1 all being available at a time. So if I have a 2 qubit system, then obviously I will have 4 basic states. We call these as states of the qubits, and these are all called basic states. And every state would also have a complex constant. We represent that with different variables. So meaning every qubit state would have a particular alpha, beta, gamma, or A00, A01, A10, A11. These are all called complex constants, and every basis state would be associated with one particular complex constant. Why do we require it? And actually, this would not be there in the case of classical. But however, when it comes to quantum, every qubit state would have a complex constant. Why we require complex constant, that we will discuss in the upcoming slides. So imagine if I have 3 qubit system, as I said, you have all possible states of 0 0 0 to 1 1 1 all being available. That means 2 power 3, that is 8 possible states, all are available to the programmer at a time or the application developer at a time. And because of that, we can see a massive parallel computation available. So I gave 3 qubits. If suppose I have n qubits, obviously I'm going to have 2 power n possible states. It appears very simple, or with a small number of n. So take an example. Imagine if I have n is equal to 64, meaning what? I have 2 power 64 possible combination. You see here, what would be the 2 power 64 number of possible states? Can somebody read this number? It's very difficult. What is this exactly? If you want to quantify this number, 16 lakh, 16,000 or 16 crores or 16 billion. So you see the number of zeros you have. So this is a very huge number, right, of possible number of states that one can have with a 64-bit quantum computer, 2 power 64, all possible states being available to the user at a time, parallelly at a time. So this availability of all possible states makes the people to solve any kind of a complex problem which are not solvable by conventional computers, that can be solved by the quantum computer. To just give a glimpse, a typical security problem, if it is taking about millions of years to solve by a classical computer, A quantum computer can solve it in a fraction of hours. That's where the problem comes, right? So next, you see another important feature of the quantum computer we said about the superposition. Superposition means what? Given a particular qubit would have either 0 state or 1 state, or it can be there in a superposition of both 0 and 1. So whereas a classical computer with a classical bit would be there either 0 or 1, whereas a qubit would be there 0, 1, and superposition of 0 and 1. That is what is the ability or strength coming from the quantum physics. So how do I represent a qubit which is in the form of a superposition? I would be representing in the form of 1 by root 2, the qubit 0 and qubit 1. This is the called superposition state. This is called superposition state. Now imagine if I have 3 qubit, then what would be the superposition state for a 3 qubit system? So you can see here 1 by root 8, 0, 0, 0 to 1 by root 8, 1, 1, 1, 1. So this is the superposition state of a 3 qubit system. Similarly, you can have an n qubit system having all qubits in a superposition state. Next, we have another important property of a quantum computer called coherence. Coherence or decoherence, especially quantum decoherence, means loss of superposition, right? When what we said superposition, a qubit could be there 0 or 1, or being there 0 and 1, right? So whereas in the case of decoherence, the quantum computer or the qubits would lose the superposition state and resulting because of the interaction with the environment. So the loss of information happens by the qubits because of the environmental effects. This is one of the reason, or this is one of the main factor we call quantum computers are extremely fragile. Next, another feature or another basis of quantum computing is the measurement, which is quite opposite to the superposition state. So when a qubit is in a superposition state, it is there in the all possible states that a qubit should be. But when you measure it, it gets collapsed, right? It gets collapsed to either 0 or 1. In the sense, a qubit will be, we said, it could be either 0 and 1 in the case of superposition. But when you measure it, it gets collapsed to either 0 or 1. But sir, whether it gets to 0, finally when I measure it, whether it reaches to 0 or whether it reaches to 1, that is based upon your complex coefficient or the variable that what we have assigned previously. A few seconds back, I've talked about the variable alpha, beta, gamma, or A0, A1, like that variables. So if the variable we have, the square of the variable decides to which state the qubit would settle down, whether it settles down to 0 or whether it settles down to 1. The square of this particular variable defines the state. So meaning, you are not sure till you measure it whether it reaches to 0 or 1. So we have talked about qubits. We have talked about the superposition of the qubits, meaning a qubit could be there in the possible combinations of the states. When you measure it, it settles down to either of the state, but to which state it settles down, it is based upon the complex variables that are assigned to each of the state. That's what we have discussed. Next, followed by the qubits we have is the quantum gates. It is similar to the logical gates that are there with the classical computers. We have the quantum gates. The quantum gates, here we have multiple quantum gates called one of the example gate that what we have is the Hadamard gate. What is this Hadamard gate is doing is it takes the single qubit as an input and put it in the form of a superposition state. So as I've already said a few slides back, if you take a qubit, it could be there in the superposition state. How do you achieve superposition state? If I apply this Hadamard gate over my qubit, it reaches to the superposition state. So gates will help us to move or to transform the given qubit data to whatever that we require. Next gate we have is the Pauli X gate, wherein which you have, if you apply the Pauli X gate on 0 qubit, it reaches the 1 state. If you apply it on 1 qubit, it reaches to the 0 state, meaning it flips the given input. That is the job of poly gate. Similarly, you have C0 gate, which is called as controlled NOT gate, and it is a 2 qubit gate. What we have seen, Hadamard gate or X gate, they are all single qubit gates. The C0 is the two works on the 2 qubits. So you can see the logical operation. If you have 0, 0, when you apply C0, it reaches 0, 0. If you apply 0, 1, if you take 0, 1, apply C0, it reaches 0, 1. Whereas if we take 1, 0, if we apply C0, it reaches 1, 1. If you have 1, 1, it reaches 1, 0. Meaning what? If I say this is my control qubit and this is my target qubit, my target is remaining same when my control is 0. But when my control is 1, my target is getting flipped. That is the job of this particular gate called C0 gate. So it acts on 2 qubits, the C0 gates. So if your control qubit is set to 0, target remains same. If control qubit is set to 1, target gets flipped. So this is the job of C0 gate. Like this, we have several gates that forms the basis or that provides the the computational ability on the quantum computers. So you have seen poly X gate, we have poly Y gate, poly Z gate, Hadamard gate, which gives the superposition, phase rotation gates, S gate, P gate, T gate, then C0 gate, control Z gate, swap gate, Toffoli gate. These are all the gates which are the fundamental for quantum computers, especially those who are from computer science or electrical or the electronic background. They all know that we have classical gates. Now, from fundamental bit, we are operating these particular gates so that we are able to run our computations, we are able to perform our calculations. Whereas in the case of quantum, these are all the gates. So you can see the different gates. And fundamentally, if you observe these gates, if you try to program, we actually play with the matrices, corresponding matrices. Meaning what? Every gate is encoded in the form of a matrix. So you provide the input and that input operates on the particular gate, means you apply corresponding matrix operation on the given input. So that is the fundamental when we do it, when we write the programs. So now we have seen qubits, we have seen Q gates. When you have multiple gates or when we have a sequence of quantum gates, what they form quantum circuit. Like classical computers, when we take the gates and when we combine them, we'll have the circuits, right? So in the similar manner, we have quantum circuits. If you see here, I have a qubit 1, I have qubit 2, I have qubit 3. Now you can see that there is a Hadamard gate, there is an S gate, there is a Toffoli gate or a T gate. Then, there is a T gate. Then, the output is getting given as an input to the next gate. So this is my swap gate, So these are all forming a quantum circuit. So similarly, if you observe this in this particular circuit, there is a diagram which talks about the measurement. So if you see here, a qubit is in Hadamard, meaning superposition. After that, it is going for measurement. So this is how we can read the quantum circuit diagrams. So now we have seen bits, we have seen qubits, we have seen Q gates, we have seen what is a quantum circuit. And when we play with those circuits, we can do that with the help of quantum algorithms, right? So we need to write an algorithm so that we can exploit these qubits and the quantum circuits. So for which we need algorithms. What are the algorithms that we can do? We have several algorithms in quantum called one. Somebody has already asked about the Shor algorithm. There is an algorithm called Grover algorithm, which is mainly meant for Shor algorithm is mainly meant for solving the prime factorization problem. Grover algorithm is meant for solving unsorted or unstructured search problem, right? So how do I search in a faster manner in a given unstructured database? So there is an algorithm called Grover algorithm. So these algorithms are fundamentally available algorithms, like there is Simon algorithm. There are algorithms like this. On top of that, people are trying to build algorithms so that we can exploit these quantum properties of qubits, Q gates, and Q circuits, right? By exploiting that Q gates or Q circuits, what is that we will achieve is, we will achieve the parallelism. We will achieve the entanglement capability. Meaning what? When a qubit, somebody has asked, two qubits can be entangled. Meaning what? Measurement of one qubit will affect the outcome of the other qubit. Meaning what? In a loose term, I can say entanglement is like a kind of a correlation. You can correlate two qubits. When you measure one qubit, obviously the outcome of the other qubit also would get impacted, right? Now, what is the difference between the algorithms that are there in a classical environment? Since we talked about the quantum algorithms, when it comes to the measurement of these algorithms, generally for classical algorithms, we talk about algorithms that we look for the algorithms that are solving the problems in a we'll say that these algorithms are deterministic algorithms and they execute or solve the given problem in a polynomial time. And the algorithms don't produce any kind of error and there is no randomness involved. Meaning what? Imagine if I perform a matrix multiplication operation, which is a deterministic algorithm, you perform any number of times, you get the same output, right? Whereas in the case of quantum, we measure them as, these quantum algorithms are measured as bounded error quantum polynomial time, called BQP time.
Sorry to
So
disturb
if
you.
you
There are
look at
certain questions. Sorry, sir, I'm disturbing you. There are 3-4 questions in the chat box. Can you address them?
okay. Wait. Yeah.
People are waiting. What are the possible research areas in the field in India?
I will. This is in.
Okay.
This is I will do that. So
Okay.
sure. So when it comes to measuring these algorithms, we look for the algorithms that run in a polynomial time. When it comes to quantum, we look for the algorithm. We say that these algorithms are bounded error quantum polynomial time. Meaning what? These quantum algorithms run in a polynomial time with bounded error. This is what is very, very important. You look at the case of classical, there is no randomness, there is no error. Whereas in the case of quantum, you are having the algorithms that run with a bounded error capability. Meaning what? Imagine if I am running an algorithm 3 times, it should produce at least 2 and above. At least it should produce 2 and above number of times correct result. Meaning what? I'm giving, in the case of a classical, if I'm running my algorithm 3 times, it should produce 3 times, it should produce the same result. Whereas in the case of quantum, there is a room for error, and which is given tolerated as a bounded error, right? So that boundness is at least 2 and above, it should be correct. That's what is called bounded error quantum polynomial time. And then this error, what will happen is we will try to reduce it by performing repeated computations. So the best examples what we have is, as I said, Shor algorithm and Grover's algorithm. Now, so how this type of images people would have seen already in the news and other magazines about how does the quantum computer look. This is generally every day we see in the news or wherever we try to see about a quantum computer. This is about IBM quantum computer, which is a 53 qubit superconductor quantum computer. If you look at the various platforms that are available now, as of now, to the academic community, there are the platforms especially coming from IBM, which is IBM Quantum, and this particular is programming interface provided by the IBM is through Qiskit, and it supports the Python. And there are various educational typical use cases for education purpose, implementing the quantum gates, implementing the quantum variational algorithms. In case of Amazon, they have a platform called Bracket. Of course, it is pay as you go, and it supports Bracket SDK. Of course, we can have the algorithms and various use cases such as optimization, as well as we can also run hybrid algorithms such as quantum classical algorithms. Even from Microsoft Azure also has a platform which is pay as you go, which supports the programming through Q# as well as Python. right? And we can, there are various use cases from quantum chemistry, algorithm simulations and all. These are all given to academia. Similarly, from Google, we have quantum AI, of course, for research purpose. There are various use cases in terms of quantum walks. There are algorithm benchmarks that are there. And people talk about quantum supremacy, meaning what? It has achieved the highest, as per the current standard, it has achieved the quantum superposition states. Similarly, it has D-Wave also has the platform. Xanadu cloud platform is there. Through Pennylian, people are writing the programs again to solve quantum machine learning problems and chemistry problems. These are some of the platforms that we have. And before I proceed and address the questions, I would like to address some of the myths general public or people have. People think that, few years, couple of months back, even people thought that quantum computing would not be commercially available for next 10 to 15 years, but it is not so. Now quantum computers are commercially available, and even whether to have a quantum computer on campus, certainly it is not required. We can access them through the cloud platforms that are already there. And that is how the researchers and government agencies and then the enterprises are trying to access the quantum computing facility. Then another myth is about a qubit can be there 0 and 1 at a given time, same time. In order to understand, even I have mentioned that a few slides back, I've mentioned that a qubit could be, a classical bit could be in a 0 state or a 1 state. When it comes to quantum, it could be in both states. What does actually meaning is that a qubit is, when I say that qubit is in the 0 and 1 state, it is in a position of superposition state, meaning it represents the value in the form of a linear combination of real and imaginary numbers that changes by a computer program or through a particular circuit. Meaning what? If I have a qubit Q1, I say 0 or 1, or it is in the form of a linear combination of 0 and 1. That is what is meaning of that. So it is either 0 state or it is in 1 state, but it is in the combination of 1 state as a linear combination of these complex variables. Right? This is what is meant by superposition state. It is not that simply we say 0 and 1. So this is another myth. Of course, the other branches of people may not be of that much pay keen attention, but whereas for a computer science students, this difference or this understanding is very much required. Quantum computers replace classical computers. People may think that, but in fact, classical computers would certainly say, take an example, if I have a typical spreadsheet program or a typical, the Microsoft Office Word program or whatever it is, I can use always my classical computers. Quantum computers are needed or required to solve highly complex problems, right, that are not solvable by the classical computers. I don't require a quantum computer to perform my day-to-day computations, my day-to-day algorithms, or to calculate my simple tasks of financial calculations and all that. So they require certain, if I have some complex problems, which I'm going to talk about after a few slides, there only you require quantum computers. It's not that, next another 10, 5, 15 years or 5 years, all classical computers will be replaced by quantum. It's another myth. Again, quantum computers solve all classical problems. This is another myth. We require classical computers to solve all classical problems. Only those problems that are not solvable by classical computers only we require quantum. Quantum computers will destroy encryption or provide, I will pass. Quantum computers will destroy encryption. Partly it is correct. Again, partly it is not, in the sense it will completely destroy or give threat to encryption algorithms such as public key encryption algorithms, not symmetric key encryption algorithms, meaning private key encryption or symmetric key encryption algorithms. Of course, quantum computers will make an impact, but they cannot destroy. Similarly, quantum computers will provide complete security. Again, this is another myth. It's not so. So it is only for computer science people or only for physics people. Again, another myth. Now we have I'm going to talk about various fields in which almost all branches of people are going to gain benefit out of the quantum computers. Right. So this is another slide which I think similar to the one which I've already mentioned about various companies that are there in the market, and they have their own quantum computers. On what technology these quantum computers are built. Say, take an example, IBM quantum computers are built from superconducting technology, whereas the other Microsoft company, Microsoft has their qubits built from topological properties. The trapped atom properties are used by Xanadu. Similarly, photonic devices are used by PsiQuantum. So like this, there are various technologies behind building qubits, and each company is using as per their requirement. Now, if you observe the quantum computing market, it is going to significantly increase globally year after year. As per the estimations, it is expected that it would touch about more than $5 billion by value by 2032 in North America alone. Globally also, it is going to touch by 2032 $65 billion. It's a huge market that is evolving in terms of quantum computing. If you observe the use cases, there are several use cases. One of the use case is about portfolio optimization. Suppose I wanted to optimize my financial portfolio in a way that I would reduce the risk. Certainly, the quantum computers would provide better solutions. Similarly, in a complex financial environments, how do I manage the risks? Again, this is also going to be provided use case by the quantum computers. Similarly, in the case of cryptography, as I said, there is a threat from quantum computers. At the same time, we are going to have some solutions coming from quantum computers towards cryptography, and finally to the security per se, the cyber security per se. And as well as the machine learning side, we are going to have quantum machine learning algorithms which are trying to augment or support the classical machine learning algorithms or optimize the classical machine learning algorithms. So these are some of the use cases. And if you see the larger use cases, several enterprises are already either becoming quantum ready or are making themselves quantum ready. You can see almost all large sector players, either in terms of financial sector, whether in terms of healthcare, whether in terms of transport sector, whether it is whether in the case of telecom, whether in the case of space technologies, whether in the case of the oil and energy sector, almost every sector, if you notice, they are the major companies, they are trying to leverage the quantum computing for their day-to-day operations, or their R&D operations, or for their future the use cases, and then the future ready purpose. And hence they are actually trying to hire as much as talent as possible. The slide shows almost all leading players in every sector. So in terms of healthcare, you can see Novartis, you can see Pfizer, you can see United Healthcare. In the case of financial, you have PayPal, you have HSBC, Morgan Stanley, JP Morgan. In the case of transport, you can see almost all leading transport companies like BMW, Toyota, Ford. In the case of space, you have Boeing, Airbus. Almost every company in every sector, they are trying to leverage the quantum computers. Again, this slide, which is taken from the infographic, is taken from the McKinsey report, wherein which you can see the various quantum computing or quantum related algorithms coming from, say, whether it is solving a factorization problem, or algorithms related to simulation, algorithms related to quantum optimization, machine learning and algorithm, and then search problem. So these are all the various algorithms or algorithm categories, and you can see various application or use case scenarios, like whether it is a finance, life sciences, aerospace, chemicals, transport, automobile and manufacturing industry, various industries. If you notice, what would be the impact of these algorithms or the algorithmic category. So especially if you look at the factorization algorithms, as I said, it is going to make a disruptive impact on the finance. The reason is simple. We perform day-to-day a lot of online transactions, banking transactions. All those transactions backbone is cryptographic algorithms. So breaking these cryptographic algorithms obviously would make a disruptive impact. That is the reason why you can see the infographic indicates that the quantum computing has a major impact on the finance. Similarly, you can also see the optimization algorithms are also going to make a significant impact on the finance. The reason is that we are going to have a low risk and better optimize our finance portfolios. Like this particular infograph, those who are interested, you can actually Google it through and ask the McKinsey report of use cases. You can get this infograph. Similarly, you can also see, this is another in terms of quantifying the business value of these, the algorithmic categories of quantum computing and in various sectors of pharma, aerospace, chemistry. You can see all the figures. Those who are from finance, management, and business sectors, you can see the business value of all these categories that the quantum computers would bring to various sectors and various algorithms. So take an example. In the case of optimization, aerospace has going to have about 20 to 50 billion dollars of value, especially for the optimization purpose itself. So these are the various use cases that we have. So among the industry sectors, the finance industry is the first or the most earliest industry adopting the quantum computer. As I said, fundamentally, number one, because of the security reasons, but also not only that, it is also about the various use cases. Within finance itself, you can see various use cases in terms of portfolio selection, capital allocation, transaction settlement. Like this, we have various use cases within the finance sector itself, right? So because of that, there are leading players in the finance sector which are deriving benefit or value out of these the use cases. Similarly, in the case of automotive, again, optimization, simulation, and numerical simulations and all, we have various use cases, right? As I've shown, BMW and other Ford and other major automotive industries are also trying to leverage this quantum computing for their various use cases of their manufacturing, optimization, and etc. Right? Especially pharma is another sector, healthcare sector, wherein which people are trying to, this particular infograph, you can see, especially the drug discovery or new drugs design. This is one of the field where people are trying from the healthcare and pharma sector to use the quantum computers. Now, India, in fact, when I was listening to the previous speaker, somebody has asked the question about which are the companies leading. I'm glad and proud to say that, even our country is leading in the quantum sector. Government of India has taken the initiative to launch the National Quantum Mission a couple of years, 3 years back, wherein which they have identified 4 different sectors to nurture in the field of quantum computing, in terms of quantum computing, materials, communications, and computing. So because of the major funding is given, and because of that, there are several startups and government entities, enterprise users, universities, investors. They're all actively contributing to the national quantum ecosystem in our country. You can see that there are various startups which are working in our country, QNU Labs or QPI or Quantum AI, like this, which are building the products from quantum computers, quantum communication related protocols, and etc. And government organizations are also getting actively involved. Universities are also actively involved in the ecosystem. Right? These are all the players which are contributing to the growth of quantum computing in our country. Quickly, I'll just show a couple of our works which we have done with our team. This is about one of our research paper that was published on dealing with the quantum aspects of high-dimensional conceptual space. Of course, I'm not going to deal or explain this in term because of the want of time. And then again, we have another work dealing with decision making in cognitive paradoxes with the contextuality and quantum formalism, which was published in Applied Soft Computing Journal. Again, quantum inspired ensemble approach for decision making purpose. Then we have about quantum machine learning related optimizing the quantum SVM algorithm for a specific case of breast cancer diagnosis. And similarly, this is another work on dealing with the quantum computing as well as the homomorphic encryption in the cryptography algorithms. These are some of the works that our team has published. And especially those if we have students and faculty wanted to convey to the community. So people who wanted to venture into the quantum computing as a career, they should first of all understand the fundamentals, acquire the proper skills, and then we can have a formal or informal education. There are a lot of resources and gain the practical experience thanks to the platforms such as IBM Qiskit environment, which is providing practical experience. And of course, the forums such as this would provide opportunity to network with the professionals. And then above all that, let us always be curious to learn things. So this would be the pathways to having quantum computing as a career. So with this, I would like to conclude my presentation. Thank you very much for patient listening. And let me actually go through the questions that people have one by one.
Yes, sir. Very first question we have, what are the possible research areas in this field in India?
What is that? I could not see that, madam. What is the question? Can you repeat?
Yeah, what are the possible research areas in this field in India?
In India, actually, as I said, there is a lot of potential. Now, as I've shown in one of my slides, where you have the government agencies, startups, the academic industry institutes, they're all working together. There are a lot of opportunities, especially if you are from a computer science. Obviously, you can venture into either number one, post-quantum cryptography or quantum cryptography. These are the two different dimensions. Of course, you can work either of them based on your interest. Then, of course, we have on the quantum communications. This is another interesting area where in which you can try to build the protocols, then building the algorithms, then quantum machine learning, or solving various problems, use cases that are already there. So these are the various research areas. Similarly, if there are people from the sciences backgrounds, such as physics and all that, materials, this is another area where people are actively working. So there are n number of opportunities. I would actually suggest you to explore based on your fundamental background. So if you know your background accordingly, I can suggest. You can write to me. Yeah.
Yes, sir. Next question is that what were the X, Y, and Z in Q gates? And please explain the corresponding metrics also. So will it be possible?
Yeah. So actually, I would actually do one thing. I will share my another lecture that is already there. X gate, Y gate, Z gate. These are all called Pauli gates. They perform certain transformations on the given input. So for each gate, there is a given matrix. So when you give an input, if I want an X operation, I have to apply the Pauli X gate in the form of Pauli X matrix. So each operation has its own meaning. It performs phase rotation. So the spin what you have seen is one will give you an understanding of what do you mean by rotation. So you can rotate it. So that is the objective of these gates. I will share my another lecture, or even you can have this recorded lecture sharing. So that would be, I think, make them understand.
Sure, sir. Sure. We will share. So one more question is that how core quantum is different from hybrid quantum?
Yeah, so this is an interesting question. A core quantum, when I say an algorithm, I'm purely working with the quantum states. Given an input, I will transform or encode it to the quantum states and then perform with the quantum gates. What is the hybrid is? It's a combination of classical and quantum. Meaning what, the QSVM part, what I have shown here, there, it is a kind of an hybrid, wherein which the entire computation goes through the classical pipeline, but for a kernel estimation, it goes to the quantum, and then the output comes back to the classical and then gets executed. So meaning what, you have a task to be done. Among that particular task, some of the steps would be executed by a classical computer, some of the steps would be executed by the quantum computer. That's called hybrid.
Sir. So one more question is there. It's Pamjot Kaur is asking. I presented my seminar on quantum computing. My teacher said that there are many environmental factors like heat impact the machine. How is it managed if I pursue my dissertation in it?
See, as an end user, so okay, I'll answer this way. Number one, we need to understand as of now the available technology, whether you are using as a student, whether I am using as a researcher or as a faculty, or an organization or an enterprise that is using the current day available quantum computers. We are all dealing with the noisy intermediate state quantum computer, meaning what we have now at the moment, quantum computers that are having the noisy environment, right? So in that regard only, if suppose I have a task for which if I have 100 qubits that are required, obviously I need to play with more number of qubits. That is what is the available state. But having said that, for a student, when you use the corresponding programming environment of Qiskit, you can always handle it through, your algorithm can manage this, the error that is coming in. That is one thing. The second thing, as I said, we also know that our algorithms are BQB algorithms, in the sense it has the bounded error. So you need to repeat the algorithm couple of times to reduce the error. So this is another factor that as a student which you need to take care when you are running your algorithms.
Same participant has one more question, sir. In portfolio analysis, is it a hybrid quantum or it will be a core quantum?
So again, when I say portfolio analysis, it's a specific problem. Now, for that particular problem, what is the algorithms that we are going to use? See, for a researcher like me, if I am using a machine learning algorithm, for that particular machine learning algorithm, so far what people are trying is, there are certain operations that requires or that can be optimized with the help of quantum, and hence we are dealing with the hybrid now.
Yes, sir. Next question is there, what are the various algorithms for quantum computing?
So as I said, the algorithms per se that is available at standard, or the Grover algorithm, Shor algorithm, these are the fundamental algorithms that are there. Now on top of that, for a given task, as a researcher, as a community, it is our job or it is our task to run our own design our own algorithms. That is the reason why recently the government of India DST National Quantum Mission call, there is an exclusive call for designing quantum algorithms. So if it is for healthcare sector, we need to design quantum algorithms. This is one of the area where in which everybody is looking for, where hardware is progressing. Again, on the software side, we need to build the algorithms.
Sir, there is last question, I hope, and the person has raised the hand. I request technical team to unmute her, Mittal, Dr. Mittal. Yes, Dr.
She's
Mittal, you
unmuted.
can.
Unmuted.
Yes,
she can ask her question.
Yes,
good
Dr.
evening,
Mittal.
sir. Yeah, am I audible there?
Yeah.
Yes.
Yes. Good evening, sir. Actually, I raised the same question in the previous session as well. Being a finance person, I mean, I'm a faculty of finance, and whatever things I'm observing as of now, like use of AI and use of this quantum computing for all the core operations that are being performed by finance professionals as of now, like portfolio optimization, construction, and so on. So, most of the students in finance do come with a non-technical background. Now, in order to look at their future and make the students prepared for all these technologies, can you guide us on how to make sure that our students are prepared to take up with all this, specifically the students who are from non-technical background and pursuing finance career?
So yeah, as I have shown this particular slide, see,
Yes, sir.
now it is all about whether I'm a finance student, whether I'm a computer science graduate, or whether I'm from whatever is my background. So now the point is that uh, uh, now if suppose if I say that I'm from computer science, I don't know what is meant by stock market. I don't know what is meant by portfolio management, right? I should know at least the basics of it, or I should know at least the basics of or fundamentals of what is happening in the finance, right? I may not be a master. At the same time, the other disciplines like finance or marketing, people should know what is happening in the technological world. And for anybody, I would actually suggest this particular pathway. Understand the quantum computer. Imagine that, what is my background? Imagine if I am from finance or from a different management or whatever is the sector, I should know what are the principles, right? I should know whatever is the relevant required skills for my this one. In the sense, if I know technology, that is fine for me based on my background. Okay, you can stop with that. In case if I am from a computer science, obviously you need to go for pursuing the formal education. Whereas a person from different domain of such as what you mentioned about finance, they may not have to actually look for pursuing the formal education. You understand the technology, you listen, you participate in the seminars like this. Similarly, interestingly, I would actually suggest, from the use cases what I have shown, you see McKinsey has given the use cases. You see the reports that are coming from the Boston Consultant, the reports that are coming from all other the firms which are leading consultation firms. They actually give any of this technology. I would suggest that they would give in a very lucid manner. See, take an example. I gave my presentation. I talked about qubit. I talked about the decoherence. I talked about representing the superposition in the form of linear combination of. But all this is not required, right? You look at their reports, they don't deal with all this technology. So
Yes,
especially if you are from a different background such as finance, I would actually suggest you to look at such reports coming from these consultation firms, which will give you a very lucid introduction to the technology, but you will understand what is happening and you will understand how it impacts. The slides that I have shown, the infographics that I have
yes,
shown, they are from those firms, right?
yes, yes, sir.
Yeah.
Yes,
Yes.
sir.
Thank you so much.
Yes, sir. Sir, it's like you delivered the concept with such a clarity and simplicity. Like this is the most complex, we can say, the concept, and you made it very easy to understand and connect with it. This topic you simplified, that is the quantum states and superposition. Like it's with a visual example such as the clockwise or counterclockwise spin you have shown, that made it very easy to understand, and the participant who were new to this subject, that was for them also it was very easy, and it's not clarified the core concept but also sparked the curiosity to explore the quantum technology further. So thank you so much, sir, for delivering such a well structured and accessible explanation. Thank you, sir.
Thank you, madam. I'm glad that it is useful, because I'm glad that there are several participants still listening even after 9 o'clock, and it's good to see their curiosity. I am happy that it is useful to them. Thank you.
Yes, thank you, sir.